So hopefully titrations, acid-base titrations, at least ring a bell from Chem 1A. But we're going to go over it anyway, because it might have been a while for some of you. So in an acid-base titration, what we have is a solution of a known concentration that we react with a solution whose concentration we don't know. One of those is an acid, the other is a base. There's lots of different variations you can have. As the known solution is added, the pH has to be monitored because there's nothing intrinsically visible that we can tell. So we can use an indicator such as phenolphthalein, and we'll see a color change, or we can use a pH meter, and then we can monitor the change in the pH. So at the equivalence point, the moles of acid is stoichiometrically equal to the moles of base, and we say that the titration is complete. By knowing the moles of acid or base that was added and the volumes involved, we can calculate the concentration of the unknown solution. Any questions? Here we have an illustration and actual pictures. Now, we've done titrations in here already, so this should be familiar. Here we've got sodium hydroxide, well, I'm assuming it's that, hydroxide in the burette and an acid in the flask. And as we add the hydroxide, it neutralizes the acid. And when we get to the equivalence point, we have just the right number of hydroxide ions to neutralize the hydronium ions or hydrogen ions. Now, whether that's 1-to-1 molar ratio for the acid to the base depends on whether we have a diprotic acid or something like calcium hydroxide, so we have to consider stoichiometry. This is what it looks like. Here we have clear solution, and it looks like we're adding water to water and nothing's happening. As we get closer to the end point, we begin to see some color change. That's because this is not mixed completely yet. We give that a swirl and the color goes away. The ideal situation is that you go from a colorless solution to a pink solution in 1 drop or less. Because when we hit this, the color change is actually the end point. That's where we detect equivalence. We want the equivalence and the end point to be very close to each other, but it's not really possible to hit it exactly. So the smaller amount of base that you add to get that permanent color change, the more accurate your endpoint will be. Now, this is a very intense color of phenolphthalein, and it's easy to get hung up on the exact shade of the phenolphthalein in your finished titration. A really intense color like this could be due to a couple of things. It could just be that this person used more phenolphthalein than was really necessary. Instead of 2 drops, maybe they put in a milliliter, right? Then just a teeny tiny bit of extra base is going to turn it really dark pink. Or they may have really overshot the endpoint. So what's more important than the exact shade of the pink, you want pale, right? Not this, that's my favorite color, but that's not what we want in our flask. More important than the actual color is how much did you add? Was it 1 drop? It's going to be fine. Half a drop, even better. You're not sure how much? That's probably not going to be good. Okay, any questions about that? So we can look at graphs of the pH of the solution as we're adding sodium hydroxide in the titration. And this is called a titration curve or a pH curve. It's a plot of pH versus volume of titrant added. So in this pH curve, we have a strong acid being titrated with a strong base. When the volume of sodium hydroxide added has been 0, so at the beginning, this is the pH of the acid solution. As we add sodium hydroxide, the pH will go up somewhat. When we get to the equivalence point, the pH shoots way up, right? And you probably observed that on Tuesday with your pH titrations. It's not really hard to find this just looking at the data because the pH jumped from like 3.5 to 11 in the addition of 1 milliliter. So The point of inflection is where the slope changes here from positive to negative. The point of inflection is the equivalence point. That's where we have a stoichiometric amount of acid and base. pH changes very dramatically there. The exact shape of this curve is going to depend on several factors: the strength of the acids and bases involved, their concentrations, etc. But this is the general shape. So consider the titration of 25 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. So let's calculate the volume of sodium hydroxide required to reach the equivalence point. So this is kind of backwards of what we do in lab, where we've got the concentration, say, of the sodium hydroxide in the HCl, and then we're trying to figure out the volume, and we measure it, right? And then we use that to calculate the concentration. Here we know the concentrations, we're going to calculate the volume instead. Well, this is really just stoichiometry. So I like to use the chemical equation to organize this information. So I've got 25.0 milliliters of the HCl, and that's 0.100 moles per liter. And the sodium hydroxide is also 0.100 moles per liter. And I'm trying to figure out the volume. And I probably want that in milliliters, right? So this is solution stoichiometry. This is what I know everything about, and this is what I'm trying to find something out about. So stoichiometry always starts with grams to moles to grams. And then we sometimes need to modify that a little bit. So here, instead of starting with grams, we're starting with milliliters. And instead of ending with grams, we're ending with milliliters. So I have 25.00 milliliters of that HCl solution. And I want to convert this to moles of HCl. I'm going to put my units in here first. Moles of HCl, moles of sodium hydroxide, milliliters of sodium hydroxide. So I've got milliliters to moles to moles to milliliters. Any questions? This should be review. I've got milliliters here, and I think we're beginning to become comfortable with millimoles. So what I can do here to make this calculation much quicker is I can say, well, let's make this millimoles, and then if I put milliliters in the denominator, right, that's the same as moles per liter. So this is 0.100 millimoles per milliliter, right? And then here, I'll put millimoles in the top and millimoles in the bottom. And what's this mole ratio? It's 1 to 1. And then here at the end, let's check our units here. I've got milliliters canceling, and I've got millimoles canceling. So I need millimoles down here, so that the millimoles are going to cancel out and give me volume in milliliters. So I'm going to use the concentration of the sodium hydroxide. 0.1 moles per liter is the same as 0.1 millimoles per milliliter, because I could just cancel out the millis and it's exactly the same thing, right? So milliliters is on top and 0.100 millimoles is in the denominator. So I need 25 milliliters. 25 milliliters for the equivalence point. It's like, well, duh, why do we even have to calculate that? Because it's good for you. The reason it's the same number is this is 1 mole to 1 mole, and these concentrations are the same. So it's going to take the same volume. Any questions? That's not usually the case. So now we're going to look at that same situation. We're titrating the 0.1 molar sodium hydroxide with 0.1 molar, no, the 0.1 molar HCl with 0.1 molar sodium hydroxide. Let's calculate the initial pH before we add any base. So initially we have a 0.1 molar HCl solution. What kind of an acid is HCl? It's a strong acid. So it ionizes completely. So it's going to make 0.100 molar H plus and 0.100 molar Cl minus. So pH then is the negative log of 0.100. Or 1. The concentration has 3 significant figures, so I'm going to say that the pH is 1.00. Any questions? Strong acid, calculate the pH. It's pretty easy compared to the buffer stuff we've been doing. So here's our little graph. And so this first point at 0 volume added, we've got the pH is 1. So we can go through and calculate all the different, choose your interval. We can calculate the points in this pH curve. What we did on Tuesday is we used the pH meter and we just measured them. So what is going to happen after we've added 5 milliliters of sodium hydroxide? So here we're going to use one of those BA tables. So here I started out with, we need to use moles here. The reason we need to use moles instead of molarity is we're adding volume. The volume keeps changing throughout the titration. And so we can look at the stoichiometry here using moles. It gets very messy when we look at volumes with everything. So what we'll do is we'll find out how many moles of hydronium ion are there, and then we'll convert to molarity at the end. So 25 milliliters of 0.1 molar HCl, I've got 0.00250 moles of hydronium ion. I'm adding 0.0005 moles of hydroxide. This would be a lot easier with millimoles. And so that's going to react. I'm subtracting this from that, and I end up with 0.002 moles of hydronium ion. We don't have to do any Ka business because this is a strong acid and a strong base. There's no equilibrium. So here's my moles of hydronium ion. I need a concentration. So there's the moles, and I have to divide by the total volume, which is the volume I started with plus the volume I added. And so that gives me a concentration of 0.0667. Then the pH is the negative log of that. Oops, I lost a 0. And this should be higher than 1. So 1.717 587, call it 1.176. Any questions? So the pH went up, right? Because the sodium hydroxide reduced some of the acid concentration. We can also calculate after adding 10 milliliters, 15 milliliters, 20 milliliters of sodium hydroxide. Let's just do one of those. Pick one. 15? Okay, we'll do this 15 one. Just going to do this one. So the others are going to be the same. So we're going to look at moles. So we're adding hydroxide ion to our hydrogen ion. We can do hydronium ion. This is just shorter. And that's going to make water. So we started with 25 milliliters of 0.1 molar. And we'll just do the little math down here. So 25 milliliters times 0.100 millimoles per milliliter. So I've got 2.50 millimoles. So this is before addition, 2.500 millimoles. The numbers here are bigger because I'm using millimoles instead of moles. I'm adding 15 milliliters of my sodium hydroxide. So 15 milliliters of the sodium hydroxide is 1.50 millimoles. So addition 1.50, yeah, I think we got an extra 0 millimoles. And so after the addition, we're assuming that this is going to react completely with that to make more water molecules. So after addition, this basically goes to 0. And what I've got left for the hydrogen ion is 2.5 minus 1.5, which should be 1.00 millimoles. Because all of this is going to react, and it's going to use up 1.5 millimoles of what I have, and so what I've got, I put it in the wrong place. I see these looks like, I don't understand, but I'm not sure if I should actually ask a question or not. Yeah. Is that better? So this is our millimoles of hydrogen ion in the solution. To calculate the pH, we need the volume. I might change to a different color so it doesn't get too confusing. My volume here is I started with 25.0 milliliters of the acid, and now I have added 15 milliliters of the base. So I think that's 40 milliliters, right? So the hydrogen ion concentration then is the number of moles, so 1 millimole divided by 40 milliliters. I'm not going to try that. It's got a 2 and a 5 in it. 0.025. Any questions? Do you see the beauty of millimoles? Those numbers are a lot easier to write down. There's a lot fewer zeros. I've looked at some, worksheets and things, and sometimes the only mistake is you put 3 zeros instead of 2, right? It's a bummer, you got the answer wrong. So this way we don't have as many zeros to deal with. So then there's our concentration. So then our pH is the negative log of that. .602. Which lines up nicely with what they've got up here. Any questions? So if we were really calculating all these points, what I would do is I would write this out once, and then you could either go in and just change a number actually physically on the paper by crossing one of these out, like crossing out this and changing it to 2 millimoles, and then change the other things. More commonly what you'll do is you'll just sort of do that in your head and come up with these answers, following this as what I'm doing, but I'm not actually showing everything. And we check ourselves by making sure that this is continuing in a reasonable trend. If this one ended up being up here, then I'd say, must have done a calculation wrong. Maybe I should write that one out. So pH after 25 milliliters of sodium hydroxide, this is at the equivalence point. Oh, let's be consistent. So hydroxide plus hydrogen ion, making water. Before the addition, I had 2.5 millimoles of the hydrogen ion. The addition is going to be 2.5 millimoles of the hydrogen ion, hydroxide ion. And then when these react, I'm going to have essentially 0 and 0 here, right? But can I have a 0 concentration of hydrogen ion? What does pure water do all by itself? It autoionizes, right? So what I've got here is that my hydroxide ion concentration is equal to my hydrogen ion concentration. And they are approximately 0, but they are not actually 0. So these are equal to each 10 to the minus 7, and so the pH here is 7. Right? Because we had acid, the pH was low. At the equivalence point, we've added just enough sodium hydroxide to neutralize the acid. And so essentially what we have here is a solution of sodium chloride. It's not acidic or basic. So the pH is 7. That's going to be true for any strong acid, strong base titration. Now we keep going, adding 30 milliliters. I didn't feel like writing this out, so I used the thing from the book. So again, the 2.5 millimoles, or 0.00250 moles. Now adding 0.003 moles. We're going to assume that all of this reacts that can react, right? But now we have more hydroxide than hydronium ion. So we're going to use up a stoichiometric amount of this, and we're going to have 0.0005 moles left. Does that make sense? So I'm going to change that to millimoles. That's 0.50 millimoles. So that's my hydroxide. So hydroxide ion concentration is going to be 0.500 or 50 millimoles divided by the total volume. The total volume is 25 milliliters plus 30 milliliters. So that's 0.00909. Does that make sense? I found the amount in moles or millimoles of hydroxide that was left over, because I've got extra of that now. And I need to divide by the total volume of the solution, because to calculate the pH, we need to know the volume, the concentration of the hydroxide ion or hydronium ion. So I could find POH. Now choose your way around the circle of pH. The POH is 2.04. And so pH is 14 minus that. .96. So up here it's just about 12. Any questions?
Yeah. For the after addition of the 0.005, how did you jump just to the 0.5?
That's a good question. So 0.00050 moles, times 1 millimole per 10 to the minus third moles. Is 0.50 millimoles. It's the same calculation as going from liters to milliliters. You don't usually do that because if you're going to use millimoles, you just start out with it. Any other questions? We can continue calculating, adding 35, 40, 50 milliliters. Do you think anybody need to see these? It's kind of getting repetitive, huh? Same idea as the last one. You find out how much sodium hydroxide remains unreacted, divide by the total volume of the solution, and find the pH. So the pH continues to go up, and there we've got our curve. So drawing a smooth line in here, this is our typical strong acid, strong base titration curve. We have an initial pH here at volume of sodium hydroxide equal to 0. Before the equivalence point, we have an excess of hydronium ion. After the equivalence point, we have an excess of hydroxide ions. And at the equivalence point, the pH will be 7. If you're titrating a strong base with a strong acid, the curve is similar. The difference is that it starts basic and goes acidic. Okay, this one is a little different, so let's just go ahead and do this one real quick. 50 ml sample of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of nitric acid. Well, let's look at our chemical reaction here. We've got sodium hydroxide plus nitric acid. We can predict the products by swapping partners. We're going to get H2O and sodium nitrate. We balance that. It's already balanced. It's a 1-to-1 mole ratio. We need to know that. I've got 50 milliliters of sodium hydroxide, and the concentration is 0.200 moles per liter. And my nitric acid is also 0.200 moles per liter. Now, I'm not calculating how much acid needs to be added for the equivalence point. I'm calculating the pH after 60 milliliters of nitric acid is added. So I've got 60 milliliters of that. So I'm going to make a BA table. I literally just made that up on Tuesday. I'm kind of liking it. So I have hydrogen ion and hydroxide ion reacting. Before the addition, what I've got in the flask is sodium hydroxide, and I'm adding nitric acid. So I've got 50 milliliters of 0.2 molar sodium hydroxide. So that's 10 millimoles of sodium hydroxide. So initially I have essentially 0 hydrogen ion, and I have 10.0 millimoles of hydroxide ion. You okay with that? The addition, I'm adding acid. I'm adding 60 milliliters of 0.2 molar. 60 milliliters times 0.200 molar is what, 1.2 or 12? 12.0 millimoles. So I'm adding 12 millimoles of acid. We could look at this sort of as a limiting reactant problem. I have 12 millimoles of this and 10 millimoles of that. I've got extra of the acid. So 10 millimoles of this is going to get used up and use up all of that. So I'll have essentially 0 hydroxide, and I'm going to have 2 millimoles of the acid left. You okay with that? See how that happened? So I've got my hydrogen ion concentration is the amount of hydrogen ion. I've got 2 millimoles divided by the total volume. The total volume is 50 milliliters plus 60 milliliters. So 2 divided by, it's 110, right? So the molarity is 0.01818, repeating. pH then is the negative log of that. .74. Now, I'm thinking about significant figures. I'm looking, all those numbers they gave me had 3, so I'm going to throw another one on here. 3 sigfigs. Any questions? It would be different if the stoichiometry was different, yes. In stoichiometry, the mole ratio is why you should never use the dilution equation when you have a chemical reaction. The dangerous thing is it works if the stoichiometry is 1-to-1, but if it isn't, it doesn't work. So let's think about a weak acid being titrated with a strong base. This is what's happening in the lab we're currently working on. So we can calculate again the volume of sodium hydroxide needed to reach the equivalence point. Here we've got formic acid. We've got 0.100 molar formic acid. There's 25 milliliters of it. And our sodium hydroxide is 0.100 molar. These are the same numbers for our strong acid, strong base, right? And how did that calculation go? We ended up with the same volume, right? This is going to go the same way. I'll write it out real quick here. Same. When you're just going to the equivalence point, it doesn't matter whether you've got a strong acid or a weak acid. This only ionizes completely, but as you take the hydrogen ions away, that shifts the equilibrium. And so you keep shifting and shifting until you've used up all the hydrogen ions from the acid. Any question? The other calculations, though, are going to be a little different because of the weak acid. So here our Ka is 1.8 times 10 to the minus 4 for this acid. The initial pH, this is, we've done a bunch of these in chapter 16. We're going to look at the initial concentration of the acid, and then it's going to dissociate or ionize. And so we set up an ice table, and we've got this relationship here. And so we can say that our Ka, which is 1.8 times 10 minus 4, is equal to x squared over 0.100 minus x. X here is equal to the hydronium ion concentration. My calculator tells me it's 0.00415. So then the pH is the negative log of that. .382. So let's look at what happens with adding 5 milliliters of sodium hydroxide. So here we have our starting amount of the acid, so 0.00250 moles, and adding 5 milliliters of sodium hydroxide, that's 0.0005 moles of the base. We're going to look at the weak acid and the strong base reacting stoichiometrically. The solution is a buffer now. So we've got this addition. All of that's going to react to form with our acid, and it's going to form some of this conjugate base. We didn't have to worry about that before. But this is a buffer, so we could use the Henderson-Hasselbalch equation. pH is equal to the pKa. pKa, let's find out what that is. .74. That's our pKa. Can we plug these numbers into the Henderson-Hasselbalch equation? They're moles. Do we have to worry about the molarity? We don't, actually, because we're taking this moles divided by the total volume of solution, and this moles divided by the total volume of solution, and we're dividing them, and so the volume, which is the same for both because they're both in the same container, cancels out. I just had to reassure myself of that. So there's our pKa plus the log of the base over the acid. I'm getting 3.14. Bless you. Any questions? So we look at the base that's added, and we react that stoichiometrically, and then this is now a buffer solution, and so we could do an ice table with the Ka and do all of that, or we can use the Henderson-Hasselbalch equation. So we can do very similar calculation, adding more and more sodium hydroxide. So we figure out moles or millimoles of hydroxide added, and we subtract that from the millimoles of acid that we initially had, and we plug those numbers into Henderson-Hasselbalch, and we get our pH. Any questions? I don't think we need to do all of those. This is the half equivalence point. That's 12.5 milliliters. We did that calculation real quick and said that at the equivalence point it would be 25 milliliters of sodium hydroxide. So this is the half equivalence point, halfway to the equivalence point. At that point, the acid and base concentrations are equal, and the pH is equal to the pKa. So this is one of the things we'll be getting from our slow titration graphs, is we can find the equivalence point and the half equivalence point, and the pH at that point should be equal to the pKa of our weak acid. And knowing the pKa of the weak acid goes a long ways towards identifying what it is. At the equivalence point, adding sodium hydroxide equal moles to the acid, we don't have a buffer anymore. We've got an anion that's acting as a weak base. So here, looking at this table, we've got our initial amount of acid, and we're adding equal molar amount of base, and so this becomes approximately 0, and then we have 0.0025 moles of the base. That's the conjugate base of a weak acid, and so it acts as a base. So we can look over on this graph here and see the pH is not 7 like it was with a strong acid. Equivalence point for weak acids is always going to be basic. How do we calculate this? That's a lot of silence. Well, we could set up an ice table, right? We've got this CHO2. So let's think for a minute. What's the molarity of that? Well, we've got 0.00250. Gosh, I hate moles. And we have to divide by the total volume in liters, right? 25 and 25 is 50, and so that's 0.0500 liters, right? .00250 divided by 0.05. So I've got a molarity here of 0.0500 molar HCHO2 minus. So I have a conjugate base. Well, this is a weak base, right? So let's treat it like a weak base and see what it does. No. Yeah, stop me when I do that. This isn't HCH. This is just weird. This is the base. My apologies. Okay, our base, CaHO2 minus, is going to react with water in equilibrium, and it's going to reform our weak acid plus hydroxide ions. So we can make an ice table here. My initial concentration, I do need to use molarities here, is 0.0500 molar, and I'm saying that the rest of them, well actually that one is 0. I'm saying that the hydroxide is approximately 0. And then this is going to act as a conjugate base and reform some of the acid, producing hydroxide. So I can set up an equation for that, right? Where I've got x squared over 0.050 minus x. What does that equal? Does that equal Ka? No. That equals Kb. This is not the equation that describes the ionization of a weak acid. This is the reverse of that, right? We would be taking this and going to that if we were looking at the Ka. So this is Kb, but we can calculate Kb from Ka. There is just no room on this slide. Ka times Kb equals Kw. So Kb up here is equal to Kw divided by Ka. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 4. I got 5.27 times 10 to the minus 7. Anybody else bother to do it? What does that represent? What is X? X is the hydroxide ion concentration. Right? We look down here. X is hydroxide ion concentration. That's our hydroxide ion concentration. We're trying to find the pH. Kind of have to remind ourselves, what were we trying to do again? We're going to take 14 minus the negative log of that. 7.72? Nope. Try that again. Negative log of 5.27 times 10 to the minus 7. POH is 6.278. Yeah, I screwed up somewhere.
Why'd you take the negative log of 5.27? That's the
Beca-
concentration.
This is the hydroxide ion concentration?
I thought it was KB.
That's the KB.
That's KB.
No, this is X. I put this whole thing into my solver while you guys were daydreaming, and I solved for X. No, KB is,
Yeah, 1.6 times 10
is 5, KB is 5.56 times 10 to the minus 11. So I found my mistake. When I plugged this into my solver, I had an extra 0 here. And so that gave me minus 7 when it should have been minus 6. And thus the POH should have been 5.2 and pH. Yeah. Does that come out right?
I got 8.21.
8.21.
Yeah.
I'm gonna double check this here. Yeah, it wasn't that simple. Okay. So doing it correctly, I get 1.67 times 10 to the minus 6. Is that what you guys got?
Yes.
Okay.
For the OH.
So that gives us a pH of a POH of 5.777. And a pH of 8.2. Took way longer than it should have, but we got there. I got there, in spite of my screw-ups. So there's a lot of pieces to that. That's at the equivalence point.